Now we can compute its group delay, which is simply d phi by d omega, by extracting phi of omega, which is beta divided by 4 plus divided by alpha square plus beta square in the denominator, multiplied by omega minus omega naught square, which comes about because of the shift theorem. So, the group delay essentially is straightforward to compute. Just take the derivative with respect to the omega. It just gives you a factor twice omega minus omega naught. Okay. So, in as much as the what is group delay? Here group delay is the analog of the instantaneous frequency. Okay. It is the partner of instantaneous frequency, the time domain quantity we call instantaneous frequency in the frequency domain. Instantaneous frequency was a constant nu naught minus d phi by dt. Minus or plus is again not the sign itself is not significant, though one should keep track of it for good reason. The analogy, the analogous quantity, the partner term in the frequency domain is group delay. For a linearly chirped pulse, the instantaneous frequency was linear in time, and for the same linearly chirped pulse, we are now making the point that the group delay is linear in the frequency domain. Linear here is linear there. So, very nice analogy for a Gaussian pulse. Let us be also conscious of that, because that is what we Fourier transform. So, the fact again and the point to underscore here is that these two quantities, the instantaneous frequency and the group delay, are not inverses of each other. That is, inverse meaning reciprocal 1 over omega instantaneous is not group delay, is not equal to group delay mathematically. Okay. Albeit both of these are linear in their respective variables of interest, omega or t. Okay. However, when the pulse we can say is rather long, that is to say what? This is what we brought about. When the pulse is, when we say the pulse is long, what do we actually mean by that? We have some measure of time, some sense of time and frequency in scales, right. So, we had E of t, okay, we resorted to proportional to e to the minus alpha t square, right, exponent of I, what did we have, omega naught t plus beta t square. What does long pulse mean? Long pulse means long, say very long. The envelope is just very extensive. With scales as 1 over the square root of alpha, not even 1 over alpha. Therefore, alpha is very small, tends to 0 for a long pulse. If that were to be the case, right, then T group from the expression over here immediately boils down to 1 over twice beta omega minus omega naught, okay, which is indeed when it becomes inverse. But this is in the limit of a continuous wave. So, what is the antonym of a pulse? continuous wave, we call this CW. So, pulse versus CW, that is often the argument or the paradigm in optics in laser emission. So, in the CW limit you would have these to be kind of inverses of each other, in which case a lot of the concepts that we have discussed like a CW laser may not relate to this, but this is one way of looking at it. The other is ultra short pulse of the kind that we are describing here, where we talk about few cycles, few 10 cycles and so on. That is to say, if T is about 3 femtoseconds like in the case of titanium sapphire pulses, then if you had as a consequence the width of the pulse designated by T here, or let us say delta T for the pulse is of the order of say 100 femtoseconds or even 1 picosecond. 1 picosecond is already plenty of cycles underneath the pulse, versus long pulse, that is 1 nanosecond, 100 nanoseconds, or for that matter a microsecond. So, in the case of these long pulses, one can envision the group delay being inverse of the instantaneous frequency, but the whole concept of something like instantaneous frequency may actually not be so relevant to discuss in the context of say nanosecond pulses, because the bandwidth, the delta omega of these pulses is pretty narrow. It is a factor of 5, 10 to the 4 or so smaller than that of an ultra short pulse. For example, if you somehow if you do what you did to a titanium sapphire laser for producing femtosecond pulses, the process called mode locking, if you did the same to a helium neon laser, a gas laser typically, then you would possibly get pulses which are 100 nanoseconds or of the order of microseconds long. I may be off, or I may be somewhere correct in the ballpark between hundreds of nanoseconds to a microsecond. Do not punish me on getting that wrong. The point is that we can make any laser operate in a mode where it produces a repeated train of pulses simply by exploiting the bandwidth, the delta nu or delta omega that is available in the emission of the laser itself. And if we put all those constituent cavity modes in phase like we did in the, you recall the diagram where we added up 6 frequencies in phase, or even if they were not having identical phi, even if phi of omega was not 0, right, it had even a linear omega dependence, it still constitutes a pulse. A quadratic omega dependence still constitutes a pulse. A well defined phase relationship between omegas is all that we ask to generate a pulse out of a laser. If we did that, right. Now, for a medium with sufficiently broad bandwidth for lasing, such as titanium sapphire, which is titanium in, it is a gemstone, right, titanium ions in a gemstone. Sapphire is aluminum oxide, but this is laboratory grown or synthesized material where you control the doping of titanium ions for example. So, in that case, the point being that we exploit the bandwidth delta omega or delta nu to produce pulses which are pretty short, of say 50 or 100 femtoseconds of FWHM, whereas if I took helium neon, popular laser, gas laser, the red laser that we use in student or even research labs, or as the case may be for a laser, the red laser pointer that we use in presentations, if we did the same and organize the frequencies and the relative phases so that the laser pointer, red laser pointer produces pulses, those pulses would have been substantially long, in which case such an inverse relationship which would hold, but we would probably not ask questions about the chirp of such pulses. They are far too long for such things, such concepts to really play an important role. Okay. Now, the second order phase produces a linear chirp in the pulse. In other words, if I now looked at, let us take a numerical example and look at it, where we have a Gaussian intensity of the pulse with a linear chirp. Now, we can get used to some units in this course, right. So, what is phi 2? Phi 2 was d 2 phi by d omega 2 computed at omega naught, right. So, the units of d 2 phi by d omega 2 define the units of phi 2. So, omega has units of radians per second, okay, and therefore, phi 2 has units of, the numerator gives it units of radians, that is the phi in the numerator, whereas the denominator has, okay, we can use per femtosecond instead of per second. It is the same, it is just more convenient, you get more tractable numbers when we do this. Therefore, natural units for this would be what did I get wrong here? We do get femtosecond square on top, and this suggests I should have per radian, okay, whereas my slide has radian times femtosecond square. Let me clarify this, I will work this out and come back to you in the next lecture. But in any case, let us look at the example where we have a Gaussian pulse of a pulse with a Gaussian intensity profile and linear chirp. In the time domain, it looks like what we have seen here, whereas in the full portrait of the pulse in the time domain, we have the amplitude function, which is this guy, whereas the instantaneous frequency is a linear function of time, as we would have expected. Now, in the spectral domain, we have two quantities, we have the spectral amplitude which is again, which remains Gaussian. The Fourier transform of a Gaussian function is also Gaussian, whereas the phase function has in this case a parabolic shape, right, and the group delay, the group delay is again linear in its variation. But remember that if we measured this in a laboratory, we would have measured very likely all this not in terms of frequency, but in terms of wavelength, in which case the entire thing would sort of gotten distorted, would have gotten distorted. The Gaussian would be a skewed Gaussian, the parabolic instantaneous or the parabolic spectral phase would again have been skewed, and even the linear group delay would not look linear here. We would have to use the Jacobian of the transformation to transform from wavelength to frequency units. Okay. So, likewise for a pulse with negative chirp, in which case phi 2 is minus 14.5 radians femtosecond square, we essentially would have had things turning out the other way around. Look at the fact here in contrast that the spectral phase function is parabolic, but the parabola essentially opens downwards as against opening upwards in the other case. Okay, and the similar behavior in the wavelength domain. And note of course also that in the case of the instantaneous frequency, the instantaneous frequency falls with time and it essentially decreases as the oscillations in the time domain also show us. Okay, so this sets us up well for the next discussion, which we will mostly carry forward tomorrow. What if, that is the what if question, if the chirp is not linear? I drop the quadratic dependence and we consider this somewhat strange pulse, okay, where phi 1, phi 0 and phi 1 and even phi 2 are set to 0, but phi 3 of the spectral phase is not 0. Whereas phi 0, okay, or phi 3 is appreciable. Earlier we had phi 3 to be 0, and for simplicity's sake we set these three leading terms to be 0 so as to diagnose what happens in this scenario. Okay, this is kind of strange, you can say. It's kind of strange in the sense the electric field shape that you see for such a pulse, where the instantaneous frequency, which owing to the fact that we have in the argument to the complex exponent we have omega naught t plus 3 gamma t cube, we have a quadratic variation of instantaneous frequency with time, but this quadratic variation now leads us to an electric field shape which looks quite strange. Strange because we are used to seeing very regular pulses. In a real pulse with the first order nonlinear chirp, or where chirp is quadratic, would also have very likely a strong linear chirp component to it. We have turned that turn off. We have turned off the other phase factors simply to highlight the impact of this, the first nonlinear term for the instantaneous frequency. Okay. So, the light wave that corresponds to an instantaneous frequency having just the quadratic term non-zero, but the linear 0 would correspond to this. That is, again the amplitude, watch out, is nearly the same, right. The amplitude is again, or the envelope is still Gaussian, we have not touched that, whereas the phase term is, it has just the linear and cubic parts alive, right. So, this is we can view, how do we view this, how do I form a good sort of mental picture or develop some intuition for this. Is the electric field going to be like looking a bit crazy like this, or what is it? So, here and hereafter we can say that a pulse gathers chirp due to dispersion in a medium. I can't avoid that. In the real world, pulses are going to be chirped, okay. But here in the context of these nonlinear chirp terms, we can look upon these, okay, to essentially be distortions to the pulse. I take a linearly chirped pulse and it say passes through some optics, and then something happens to its electric field, and if the phase profile isn't quadratic and the instantaneous frequency isn't just linear, the instantaneous frequency gathers a t square type of behavior, then we would consider this a distortion over a linearly chirped pulse. So, the linear chirp, the linear term in the instantaneous frequency is strong, and these are expected to be distortions, which is to say that the value of gamma therefore okay, has to be considerably small, but that is the sense in which we expand the phase terms as a Taylor series, right. So, let us not lose track of that the phi of t term, let us keep in mind in the time domain is phi naught plus phi 1 times t plus, or let me write it like that, phi of t, phi naught important but not always, phi 1 times t plus phi 2 times t square. We should have had this diminishing in their amplitudes. Then this is a sign of what we have been building a picture of. We would call this a well behaved pulse. That is a well controlled pulse. You put in any adjective to it. It is not necessary that lasers have to always produce well behaved and well controlled or nicely shaped, whatever adjective you wish for the pulses to be given. We have to put in the effort to design and realize such a system. As I mentioned, one family of the most advanced lasers, which are also large facilities, free electron lasers at the state of the art today do not produce well behaved pulses, although they produce very short pulses. They are therefore said to be, we associate terms like noisy with it, because we do not have the control. This is essentially what this is a consequence of the fact that a free electron laser has no optical cavity. It is a mirrorless laser, if you wish. Okay. It is the cavity that adds, if you wish, shape and beauty to these pulses, which makes these pulses controlled, repeatable and so on. But of course, not just that, one needs to work a bit more, but that is the thing with the resonator which brings in. So, we can therefore treat for these pulses emerging out of an optical resonator, we can expect them to be well behaved, well controlled, in which case the higher order terms in the temporal and spectral phase functions can be considered as distortions occurring to pulses which were otherwise close to being linearly chirped. So, we would therefore call keeping gamma as small as possible in a real world scenario, we would look upon this as the management of the chirp of the pulse. How do I manage to keep the chirp linear throughout in building my laser or doing an experiment? We will later on see, albeit probably only briefly in this course, that we can manage linear chirp well, because it is a question of having media normal versus anomalously dispersive. Actually, it may be difficult to find anomalously dispersive media among naturally occurring substances over very substantial bandwidths, but a pair of gratings can actually help us, or some specially designed mirrors which are called chirp mirrors, right. But then we would want in every scenario to keep pulses and their chirp to be predominantly linear and view the rest as distortions to the pulse which occur due to propagation effects and optical elements. Okay, so that is a prelude to nonlinearly chirped pulses and putting them in some kind of perspective. With that, we will stop for today, and we will I will have a bit of time to take any questions at the moment. Any questions? Everything is clear. Okay, very well, good. Thanks then for coming in today.